Hey everyone, welcome back. Ready for another deep dive.
Always.
Today we're tackling something pretty mind-bending. Quantum theory.
Oh, yeah, we're going quantum.
But don't worry, we're not going to get too lost in the weeds.
Uh,
We're going back to the very beginning with Max Planck.
Planck, huh? A true pioneer.
Absolutely. And we're going to explore this fascinating puzzle that had scientists scratching their heads back in the day. Black body radiation.
Sounds intimidating, but trust me, it's a wild ride.
It is. And to guide us, we've got excerpts from a book all about Max Planck.
All right, so we're diving into his life, the historical context, and the science behind his breakthrough.
Exactly. So let's start with the simple question. Why does a hot object glow? You know, like a fireplace, a light bulb, the stars?
It's a question we've probably all pondered at some point, right?
Right. It seems so basic, but it unlocks this whole world of physics.
And that glow, well, it's actually electromagnetic radiation.
Hold on. So we're talking about the same stuff as light and radio waves.
Exactly, just at different frequencies. It's all around us, even left over from the Big Bang.
Okay, wait. You're telling me the faint afterglow of the Big Bang?
The cosmic microwave background radiation.
Yeah, that's the one. You're saying it's basically the same thing as the heat coming off my coffee mug.
It is. It's this constant hum of energy throughout the universe. Pretty mind-blowing, right?
It is. But let's rewind back to the late 1800s. Scientists were wrestling with how this radiation worked, especially with something called a black body.
Ah, yes, the black body.
Okay, what exactly is a black body? It sounds kind of ominous.
Imagine an object that absorbs all light and radiation that hits it. No reflection at all.
So basically, it's invisible unless it's heated up.
You got it. Then it emits radiation based solely on its temperature.
I'm picturing like a stealth ninja, invisible until it heats up and starts glowing.
That's a pretty good visual.
Yeah.
But the problem was the physics they knew at the time, classical physics, well, it predicted the black body would release an infinite amount of energy at high frequencies.
Okay, that doesn't sound right.
It's not. Obviously, that's not what happens in reality. It was a huge problem they called the ultraviolet catastrophe.
Ultraviolet catastrophe.
Okay.
So this is where Max Planck comes in, right?
That's
Our
right.
sources describe him as this meticulous physicist, obsessed with finding fundamental truths about the universe.
He was. But what's interesting is that Planck also had a surprising artistic side. He was a very accomplished pianist. He even helped evaluate a harmonium, a type of organ, for his institute.
I love that, a scientist who appreciates the arts. It reminds us that these brilliant minds aren't just one-dimensional.
Right.
But let's get back to the ultraviolet catastrophe. How did Planck tackle this physics puzzle?
Well, he initially tried to use classical physics, the physics of the day, but he kept hitting a wall.
So what did he do?
In 1900, he came up with a truly radical solution. He proposed that energy, instead of flowing continuously like a river, was actually bundled up in tiny packets. He called them quanta.
So instead of a smooth stream, energy comes in little bursts.
You got it. Each quantum has a specific energy determined by its frequency.
That's a tough one to wrap my head around.
It was a radical idea. He captured it in his now famous equation. E equals h nu.
Okay, break that down for me.
E is energy. Nu is frequency. And h is a tiny number now known as Planck's constant. It seems simple, but it completely overturned centuries of scientific thought.
So what does it actually mean that energy is quantized? What are the implications beyond solving this black body problem?
Well, imagine a staircase. You can only stand on specific steps, not in between. That's what quantized energy is like.
Okay, I think I'm starting to see the picture here. It's like the universe has these built-in rules for how energy behaves, and Planck was the first one to glimpse those rules.
Exactly. It was a huge leap forward, though even Planck himself had trouble with the implications at first. He thought of it more as a mathematical trick than a fundamental shift in our understanding of reality.
It's like he stumbled on the secret door, but wasn't quite ready to walk through it.
And the rest of the scientific community, they weren't convinced either.
So who finally took that leap?
It took another revolutionary thinker, Albert Einstein. He truly solidified Planck's ideas and showed just how powerful they were.
Okay, now that's a story I can't wait to hear. So hold on, everyone, because we're about to dive even deeper into the quantum realm, and Einstein is joining the party. Okay, so we've got Planck shaking things up with quantum theory, but our sources also show he lived through some really intense times, especially during the World Wars.
Oh, absolutely. It's fascinating to see how he navigated those turbulent years, personal tragedies, moral dilemmas, all against the backdrop of a world in chaos.
Yeah, it really humanizes him. Reminds us that even these groundbreaking scientists are deeply affected by what's happening around them.
For sure.
Our sources mention Planck signing this Manifesto the 93, defending Germany's actions in World War I.
Yeah, that was a big deal at the time.
Later, though, he expressed regret for that, especially as the war's atrocities came to light.
It seems he was torn, like many at the time, between patriotism and the horrifying reality of war.
Makes sense.
But throughout all of it, his belief in the international nature of science never wavered. He even stayed in contact with physicists from opposing countries. He was convinced that science transcended national borders.
That's pretty remarkable. Holding on to that idea of science as a unifying force, even in the middle of a global conflict.
It speaks to his character, for sure.
But then World War II brought even more personal tragedy for Planck.
Oh, yeah.
His son, Erwin, was executed by the Nazis.
For his involvement in a plot to assassinate Hitler.
It's a stark reminder of the human cost of war.
And the incredibly difficult choices people faced under such a brutal regime.
Absolutely. And Planck himself had to walk a tightrope during the Nazi era.
He did.
He opposed their policies, obviously, but he also felt strongly about preserving German science.
He tried to shield Jewish scientists, protect institutions, but it was a losing battle.
He even appealed directly to Hitler about the treatment of Jewish scientists.
You can imagine how that went.
It's a testament to his integrity, though, speaking out, even when it put him at risk.
Sadly, his efforts were mostly in vain. Many brilliant minds were forced to flee, and German science suffered irreparable damage.
It's a dark period, no doubt. But Planck's story, it reminds us of the courage it takes to stand up for what's right, even when facing overwhelming forces.
Right.
Okay, but amidst all this turmoil, personal and political, Planck's scientific legacy continued to grow. Remember Sachendra Nath Bose, the physicist who blew Einstein's mind with his paper?
Of course. He's the Bose in Bose-Einstein condensate. That state of matter where atoms act like one giant wave.
Yeah.
Crazy stuff.
Yeah. Bose, back in 1924, did something incredible. He rederived Planck's law,
Oh, wow.
but using a totally different approach, based solely on quantum principles.
So a more elegant, more conceptually sound way of understanding blackbody radiation, all thanks to quantum theory.
He basically solidified Planck's work, but also took it a step further.
Exactly. And what's really fascinating is that Bose's work highlighted a fundamental difference between classical and quantum particles.
Okay, now this is where I usually get lost. So break it down for me. What's the difference?
Imagine you've got two billiard balls. They're distinct, right? You can always tell them apart, even if they're identical. That's how particles work in classical physics.
Okay, makes sense. So what's different in the quantum world?
In quantum mechanics, particles of the same type are indistinguishable. It's like they lose their individual identity. You can't label them A and B.
So two electrons, for example, are fundamentally the same, no matter where they are in the universe.
It is. And this indistinguishability, it has huge implications for how particles behave. It's one of the core things that sets quantum mechanics apart from classical physics.
Mind officially blown. So Bose's work, it wasn't just a neat mathematical trick.
Nope.
It actually deepened our understanding of quantum theory on a fundamental level.
Precisely. And it paved the way for even more groundbreaking discoveries in quantum mechanics.
Amazing. But we can't forget about Planck's other contributions. Beyond his quantum work, he also made huge strides in thermodynamics, the study of heat and energy transfer.
He was a multifaceted physics superstar.
Right. And get this, he developed a system of units based on universal constants, like the speed of light and his own constant, h. They're called Planck units.
Planck units. Yeah.
Sounds intense. What are those used for?
They describe the universe at the smallest scales imaginable. Things like the very first moments after the Big Bang. We're talking lengths billions of times smaller than an atom.
Wow. So in a way, Planck was setting the stage for future generations of physicists to explore realms we can barely even comprehend.
Exactly. His work wasn't just about describing the universe. It was about finding its underlying code, its most fundamental building blocks. It's a legacy that continues to inspire awe and wonder today.
It's really remarkable. From the tiniest particles to the vastness of the cosmos, Planck's influence is undeniable. But you mentioned he also had a philosophical side, right?
He did. Planck grappled with profound questions about the nature of reality, especially in light of his own discoveries in quantum mechanics. And that's where things get even more intriguing.
Okay, so you mentioned Planck's philosophical side.
Yeah.
I mean, his quantum discoveries were so revolutionary. I gotta know, how he wrestled with those implications, for like the nature of reality itself.
It's really fascinating. You see, even though he laid the groundwork for quantum theory, which is all about uncertainty and probability, Planck himself, he never really let go of this idea of a fundamentally ordered universe.
So he wasn't totally on board with the randomness at the heart of things.
Not really. He saw the probabilistic nature of quantum mechanics, like how we don't know exactly where a particle is until we measure it. He saw that as a limitation of our understanding, not necessarily the ultimate truth.
So he thought there was like a deeper, more deterministic theory out there just waiting to be discovered.
Yeah, he believed that. Even as evidence for the inherent randomness of quantum events, grew stronger and stronger.
And he held on to that belief, even while debating with Einstein about it. Didn't Einstein famously say, God does not play dice with the universe?
That's the one.
What a clash of titans. But it's amazing how those debates really pushed science forward.
Absolutely. It forced physicists to confront the philosophical implications of what they were discovering, led to a deeper understanding, opened up new avenues of inquiry.
And speaking of pushing science forward, our sources point to another mind-boggling aspect of Planck's work, Planck units.
Ah, yes. Planck units, like creating a measuring stick for the universe at its most extreme scales.
From the Big Bang to black holes, right?
Yeah.
But what are Planck units?
Think of them as the universe's natural units, based on these fundamental constants, like the speed of light, Planck's constant, the gravitational constant. And they define things like the smallest possible length, the Planck length, which is billions of times smaller than an atom.
It's mind-blowing to think Planck was envisioning the universe at scales we can barely comprehend.
He was truly ahead of his time.
So it all started with this seemingly simple question. Why do hot objects glow?
Right.
And it took us on this incredible journey through quantum mechanics, philosophy, and the fundamental nature of reality itself.
Planck's legacy, it's multifaceted, right?
Absolutely.
He's not just the father of quantum theory. He's also a symbol of scientific integrity, resilience, and the power of human curiosity.
A great reminder that even the smallest sparks of curiosity can ignite these revolutions. Revolutions that change our whole understanding of the universe. And who knows, maybe one of our listeners will be the next Planck, uncovering some groundbreaking discovery that rewrites the textbooks.
Until then, keep exploring, keep questioning, keep diving deep.
Thanks for joining us on this incredible deep dive into the world of Max Planck and the birth of quantum theory. We hope you've enjoyed the journey as much as we have.